The next speaker is Hwang. He's with the EMC laboratory of Missouri as an assistant professor. He received his PhD degree at Geist in 2012 and worked at Samsung Electronics as a senior engineer from 2012 to 2015. He has co-authored more than 50 IEEE journal and conference papers and received the Best Paper Award at the AP Asia Pacific EMC Conference in 2017, at the DesignCon in 2018 and 2019. His research area includes signal power integrity, RF desensitization, and EMI. Thank you. The floor is yours.
Thank you very much. Good morning, everyone. I'm glad to be here. I'm Hwang, a faculty member at Missouri SNT. And this talk, let me touch on this PCB decoupling. And I have to mention that this credit should go to Dr. Jim Juniak. Most of this slide from his work. So, assuming there might be some PI engineers, but assuming you guys don't have any background, let me start off with these basic concepts for this PI, and then still we can apply this basic concept to very complicated multi-layer PCB design. So let me introduce some design considerations for this complicated PCB based on the same basic concepts. So let me talk about the PDN, power distribution network. So as you can see here, this is a picture of high-speed PCB board design. And you can see that there's a lot of components. And surprisingly, most of the components are actually capacitor, right? Of course, there is a CPU or PMIC, but most of these components are actually capacitors. And then if you see more kind of illustrations here, so we have some power layer inside this PCB and many decoupling capacitors on the top or on the bottom, and then this voltage regulator module. So one question is, why do we need these power layers and so many decoupling capacitors? Can you just put one or just zero? Why do we need to put this many decoupling capacitors? Seems they are doing nothing for these circuit operations, but we always have to put these decoupling capacitors for this high-speed digital board. So let me first talk about the internal circuit operation. Here shows the internal circuit. We have simple inverter. Let me say this is CMOS transistors. So when logic, this logic is driving the load. When logic switch from logic 0 to logic 1, this PMOS will be on, this MOS will be off, charging the current to this load. So there will be a charging current drawn from the power. At the same time, nothing in real world operates instantaneously, right? So there should be some moment that both PMOS and MOS are on at the same time. A very short period of time, but there is a very short time that both of them are on together. So there will be a shorting path from the power to the ground, and this current is called the shoot-through current. So because of these two mechanisms, we have very sharp current from this power net, and then when the logic changes from the logic 1 to 0, the charge stored in this load will be discharged through this MOS, the pull-down network. And then at the same time, like here, there will be a moment that both PMOS and MOS are on at the same time, so there will be a shoot-through current again. So this case, we also have this small triangular-shaped current because of this shoot-through current. So the important thing here, or what we need to remember, is that the current drawn by these CMOS circuits can be represented as these triangular-shaped pulse, right? And then this is the operating frequency. So suppose your circuit is operating at 1 gigahertz. The clock period is the 1 gigahertz. But if you look at the current, actually your period has been doubled because it draws the current at the rising edge, it draws the current at the falling edge. So period for this current actually has been doubled, right? So that is something interesting for this power kind of integrity engineers. So clock frequency and then the current actually circuit draw from the power could be different. And then why PDM matters? So here shows the simple illustration for the simulations. Suppose you are circuit engineers, you build some interesting circuit, and then to check the operation of this circuit, you put an ideal voltage supplier right next to your circuit, right? Connect your power to positive node, connect your ground to the negative node. And then usually people don't pay attention to this power supply voltage. This is actually voltage source, right? And then, anyone remember the IV curve of this voltage source? I always ask this question to our student in an electronic class. So suppose you have I and V. And then resistor is simple, right? Resistor has the linear IV characteristics. How about this voltage source? So voltage source has a vertical line, right? Voltage doesn't change, but it can provide any current. So you just put the voltage source there, but it has a lot of meaning inside this symbol. So it can provide any current this circuit wants, but without any changing of voltage, right? So in your circuit simulation, you already assume this power doesn't change at all, no matter how much current the circuit draws. But how about in reality? So of course, we cannot put an ideal voltage source right next to your circuit, right? Your circuit is inside your IC, and then package and some PCB board, and goes to the VRM, right? There is a physical path from VRM all the way to your internal circuit. So let me show that effect in a very simple circuit. So we have this power source. Let's assume an ideal power source. And then between the source and your circuit, there is some impedance. So let's say 0.2 ohm. So 0.2 ohm is pretty small values, right? But when your circuit draw 1 ampere, the voltage draw across this impedance is just 0.2 volt, right? And then the voltage your circuit sees is actually 1.6 volt, which is quite different from the actual power supply voltage you assumed, right? So this is about why we have to care about the PDN, power distribution network. We need to care about how power will be provided from the VRM to the internal circuit. So one way we can do is just simply minimize this impedance, right? If you can make a 0. Of course, it's impossible in reality. You may make a 0.001, but this impedance is from the VRM to your IC. That is also impossible. So, and then if possible, that will cost a lot of money, which engineers or your manager doesn't like. So here comes the decoupling capacitors. So what does the decoupling capacitors do? So here is your VRM far away, and then this is your internal circuit. So when you draw the current from this external far away voltage source, there will be a huge voltage drop. So we add a capacitor here as an intermediate power supplier. It can provide charge or current to the internal circuit. So we can draw the current from here and assume there is no impedance at all, then we can provide an ideal voltage to the internal circuit, right? So we may say this capacitor actually decouples a load from this power supply voltage, right? So that's what decoupling capacitors does. It can decouple this load into your circuit from the external power supplier. So we can provide more stable power or voltage to the internal circuit. So we need to think about the decoupling capacitors, the electrical characteristics of these decoupling capacitors. So a good thing in this power integrity is that we just do LC circuit analysis, not electromagnetic wave things or complicated numerical simulation. We can just do a simple LC circuit calculation and get a quite good physical insight. So here we need to understand this decoupling capacitors. So usually it can be represented as LRC, series circuit. And then we know that impedance of capacitor is 1 over j omega c, and impedance of inductor is j omega L. So we have this is a log-log scale. So we have linear negative 20 dB per decade curve here, and positive 20 dB per decade curve. So if you see this curve in an impedance profile, we can see that this is capacitive region dominated by the capacitance. This is inductive region dominated by the inductance. So here there's multiple decoupling capacitors bearing this inductance. So because this is j omega L, higher inductance, we have higher impedance, right? The slope gets higher and higher. Here shows the decoupling capacitors with bearing the capacitance. So this is 1 over j omega c. So higher capacitance has the impedance curve. So this will help us a lot to understand how PDN behaves. So let me talk about the low frequency behavior first. We just need to understand this LC circuits. Looks quite simple and straightforward, right? So one thing I have to mention here, all of these are from these decoupling capacitors. But this capacitance C plane is from the capacitance between power and ground plane. So here comes the role of this power layer. It can provide additional capacitance to this PDN network. So here shows very simple example. We have one IC and 2 decoupling capacitors, and we will talk about the impedance here seen by this IC. So assuming we are the IC and they're looking into the PDN. So what impedance we're gonna see here? So simple circuit for this PDN, we have 100 picofarad capacitance from the power ground layer, and then one LC circuit from this decoupling capacitor, and the other LC circuit from this decoupling capacitors. So here shows the impedance profile seen by this IC. So this is kind of very typical impedance curve you may see on your PCB design. So first, higher impedance means that if you have some current at this frequency, the voltage is simply impedance times current, right? So higher impedance, there's high risk that you have large voltage fluctuations. So of course, in this impedance curve, lower impedance is the better. So let's first start off with this low frequency. So very low frequency, we can neglect this impact of this inductance, right? Because they are j omega L. Omega is too low. It's, let's say, very close to 0. Then we can neglect this 2 inductance effect. And the impedance we see here from this port is the summation of 3 capacitors, right? Summation of these 3 capacitors. So now we have this negative 20 per decade curve, right? That's the capacitive curve. And then series resonance kicks in. Here you can see that first at this frequency, this LC circuit will resonate, and then in a series resonance has some kind of very sharp dip in the PDN impedance profile. You can see the first series resonance from this branch. And after this branch, after this series resonance, the effect of this capacitor has been gone, right? The impedance from this capacitor is too low, right? After this resonance, we don't need to consider this capacitor in this PDN anymore after this series resonance. So we can eliminate that capacitor. So after this series resonance, we have a parallel resonance here, which is formed by these two inductances and this capacitance. Okay? And after that, this one is also the capacitive curve here. And now this effect of this capacitor has been gone. We see only 10 picofarad plus 10 nanofarad here. That is the capacitance from these two capacitors. Okay? And after that frequency, we have another series resonance. And in this case, this series resonance is from this branch. And after that, this capacitance will fade away. So we see the inductance behavior again. And this inductance is actually 0.75 nanohenry, because this impedance is pretty low, this impedance is pretty low. So equivalent circuit we see from this node is two inductance in parallel, right? So having these two inductance in parallel, we have 0.75 nanohenry. So it shows the 20 dB per decade again. And then lastly, this inductance will resonate with this capacitor. They are in parallel. So we see this parallel resonance. After that, we only see the 100 picofarad effect. So it's all about the LC circuits, right? But based on this LC analysis, we know in this region it's dominated by all the capacitors, right? And here, that's the first series resonance from this branch, and this dip is from the resonance from the second branch. And then here, this inductance is from all this branch. And after that, we only see the capacitance of this C plane, right? So it makes us quite easy to understand this PDN behavior. So that's about the lumped capacitors. And then for PDN, the most important electrical characteristics is inductance. So inductance impedes the flow of current. So it's associated with current. So to understand how inductance change, we need to trace the current path and see how this current path changes. So when you design the PDN, we may say we are designing inductance. So what we all do here is to reduce the inductance so that we can satisfy some target impedance. And then for these decoupling capacitors, many geometries are associated with these decoupling capacitors, like package parasitics, bonding pad here, bonding pad, and the board traces and the vias. They are all attributed to this inductance. And then we will see two response. One is the impedance, and the other one is this is just LC resonator, and then the natural response of this LC resonator can be seen as these simple equations. We don't need to know these equations, but we'll see how this LC impact on our circuit behavior. Let me first see the cross-section of these decoupling capacitors. We have this multi-layer PCB and decoupling capacitors on the top. Like I said, this inductance is associated with current path. We need to look at the current, how current flow in this geometry. So first, inside the decoupling capacitors, usually there are a lot of layers interdigitated together. So current on these physical layers will cause the inductance. That inductance is actually called ESL, effective series inductance, that you can see on the data sheet. And then not only this inductance, but there are another inductance from this geometry. The first one is we call L above, because if you see the current path here, the current goes up and come down. This small loop also caused some inductance, and we defined it as a L above because this is above the power ground layer. And the other inductance is the L via caused by this power via. So we need to find the loop here to define the inductance. So first, current come down through this via as a conduction current, and it should go back, right? How it can go back? So it can go back through this displacement current. Through the E field, it can go back to the reference. So by having this loop, we have another inductance called L via. So we will analyze all these three to minimize the PDN impedance. And then from this fact, we can kind of say good design, bad design for the decoupling capacitors. First, here we have, this is the capacitor pad and the via. So we might say this is a good design in terms of inductance. And then this could be better design. Why this is better than the first one?
Mutual inductance is higher.
Right. So, right. In other words, we decrease the area. Right, exactly. We reduce the L of this portion, the L above. So larger the loop, the larger the inductance. Smaller the loop, the smaller inductance. So by putting these two vias together, we can reduce this inductance. It's quite straightforward, right? So this design could be the best, simply because distance between these two via is the smallest, right? So we can have the smallest L above. So along the same line, this design is bad because the via is far away right now. It will increase the L above this inductance. And of course, this design is ugly because the long trace, because of long trace and the vias are far away, this L above will be huge. It could be even greater than the ESL. So this PCB design, this pad design is pretty important for these decoupling capacitors. So next thing, also kind of intuitive drawing, the impact of the distance between the IC and decoupling capacitors. So you might know the closer the better. We always ask to put the decoupling capacitors closer to the IC, as close as possible. But why? So we can think about that from this, again, the current loop or current path. So first case, the decoupling capacitor is a little bit far away from the IC. So by tracing the current, the loop formed by this current is pretty kind of larger than this one. So this one, we put this decoupling capacitors right next to the IC. So by having these capacitors next to the IC, we can decrease this area, the area formed by this current loop. Then we can decrease the inductance. So having this IC very close to decay very close to IC, we see that this red curve has lower inductance, right? This is 20 dB per decade curve. And lower curve means lower inductance. And then retro response, we can provide higher current by having this lower inductance. So next thing is kind of more interesting thing to look at. So first, we have two same configurations IC next to decoupling capacitors. But their performance could be quite different depending on how you place the power via and ground via. So first case, we put the power via between these two. So they are connected to the power on the bottom. And then on the right, we put the power via outside of these two components and connected to power on the bottom. As you can see, as following this current loop, their area is quite different, right? Again, it's about the current path and the loop formed by this current. So they're quite different. So this gives us much less area, right? So much less inductance. Second thing could happen for the IC on the top, decay on the bottom. So same placement, but different power ground via locations. By having this, we have smaller area in these configurations. And then in this case, the area is kind of huge. So we can see that this design will be much better than this. So not only for the locations, but it also depends on how you assign the via, where to place power via, where to place the ground via. All these matters. And multi-layer board is the same approach applies here. So you may ask which one is better, capacitor on the top, capacitor on the bottom. Always the engineering answer is it depends. But instead of say it depends, we can give more insightful guidance, the guide for the cap placement. Here, power bus is close to the top. Then the area formed by the current path for this top capacitor is way smaller than the area for the bottom cap. However, when the power bus is close to the bottom, this area is way smaller than that, right? So we can make a very simple conclusion that we should place the decap on a side closer to the power layer, right? If the power layer is close to the top, we should place the decoupling capacitors on the top. If a power layer is close to the bottom, then it's better to have decaps on the bottom. But all this comes from the same physics. So we need to reduce inductance, and inductance is associated with this current path. We just need to look at the area formed by this current path. So let me introduce some design considerations for this multi-layer PCB design. So by the way, do you have any questions so far? Yep.
So the only hope of providing high frequency capacitance for impedance is just the distance between power and ground of the PCB. That's what it sounds like. Is that right? The other one you are dealing with the inductance of the.
Right. So.
Which makes it very difficult in the sense that, I mean, in these days you cannot make the board 10 and then it increases the cost, doesn't it?
So there's a couple of ways to reduce this inductance. Here, we're only talking about the decoupling capacitors.
Yeah.
That's why I introduced that concept.
Okay, on your circuit you showed that 200 picofarad that had no inductance.
Right.
It seems to me that's the most effective one for the high frequency.
So high frequency, I will introduce that later. But the most critical thing is how you connect your power ground to your package. We haven't considered that here, but the higher frequencies, the most critical geometry is between your package and then the power ground plane, how you connect these two. And these things can be relatively for low frequency. And then another thing I want to mention here is that inductance is always there, no matter low frequency or high frequency. But as frequency increase, it kicks in. But it's always there. Yeah, any other questions? Yes?
What about the delays that are induced by this decoupling capacitors? If you put a lot of decoupling capacitors, there should be a lot more delays.
So you're talking about the delay. So this is the frequency concept. You might get confused about this, but usually for higher frequencies, we put the decap very close to the IC. So between them, there will be low inductance. So high frequency can be covered by this low inductance path. And for lower frequency, we have high volume capacitors, but a little bit far away. So between them, there will be a relatively larger inductance. So low frequency can be covered by that decoupling capacitors. Did I answer your question?
What I was thinking is like, so when we are like transmitting some signals and we are putting like high frequency capacitors, so they have some RC time constant, so there will be like charging time.
So, yeah, you might understand this way. They are pretty small. RC constant for the high frequency decap is extremely small. So actually, you can think there's no RC delay things for the high frequency decoupling capacitors. But low frequency, the inductance matters. So that's why we put multiple decoupling capacitors to cover wide frequency range. Okay. So let me talk about the target impedance here. So everybody knows the Ohm's law, right? Voltage is current times impedance. So usually we have noise voltage specifications for the board design. And then assuming we know the exact current, we can engineer this PDN to satisfy these voltage limitations. But many cases it's quite challenging. One reason is that knowing the exact current waveform is difficult because the operation of this IC itself is quite complicated. We cannot simulate all the scenarios to cover all possible situations. And then sometimes it's their IP, they are not allowed to share this exact current waveform to PCB designers. And there are in-house tool or commercial tool to extract this current profile from the IC circuits, but it's not that practical for this PDN design. Another way we can do is assume the current profile is kind of very simple triangular shaped pulse. Like I shown in the very beginning, the current drawn by the circuit looks like the triangular shape. So we just assume there's a triangular pulse current, and then based on that, we can design some PDN. And then by taking the IFT, we can convert that into a voltage in time domain. But all of these are quite not practical for the PCB design because when you change the decap, you cannot check the voltage every time. You don't have enough information for do that, and then this process is quite troublesome. So the most common way in industry is using target impedance. So first, we define the target impedance, and whatever PCB design can satisfy this target impedance might be set good to go. So this target impedance, surprisingly, there's no actual physics or mathematical background between this target impedance and actual voltage fluctuations, right? So target impedance is believed to be a solid concept, but think about it, the voltage specifications is defined in time domain. And then this impedance and current are in frequency domain. So they are not the same physical quantities, but we define this target impedance in frequency domain. Yes?
Question, why is the target impedance going up at 700 megahertz?
Right.
It's just because it's not needed anymore, it's so low for the frequencies.
There are many, right, what you said is correct, and there are many reasons. One is it used to be a flat, but if you use the flat target impedance, no design can actually satisfy that flat impedance, because at some frequency, because of inductance, it will goes up. We cannot make the impedance flat all the way to the maybe 100 gigahertz. Right? That's impossible. That's the first thing. Second thing is it's more physical, because this PDN is dictated by the inductance, and this curve is actually usually 20 dB per decade. So they kind of define the maximum inductance that this PDN can have. So it's kind of an engineering concept, but it carries some physics. So that's why this PDN, the target impedance, has been used a lot in. Okay, so yeah, I should go fast. So there are a lot of PDN considerations. So where to place this power layer, or how large that should be, or should we use special materials? All of these questions can be answered based on the target impedance and then current physics, because that is the main factor dictating the behavior of this PDN. And then from the same perspective, will there be an effect of other ground or reference plane? In this case, we have just one power plane. Will there be any advantages having this additional reference planes or ground planes? No, because we are talking about the current path, and it does not provide any additional current loop, right? So we should have either smaller current loop or multiple current loop to minimize the inductance, but it doesn't help anything. And then where we place the decoupling capacitors, on the bottom or top underneath the IC? So we have to look at the current path. If the power layer is close to the top, it could be better to place the decoupling capacitors on the top. The other case, if the power plane is near the bottom layer, it will be better to have decoupling capacitors on the bottom. And the same thing for this question. And then, how many decoupling capacitors do we need, or it should be close to the IC, or the size of decoupling capacitors? All of these are related to inductance. Surprisingly, you can answer all these questions based on inductance analysis to satisfy that target impedance. So, key point for the PDN design is that use this target impedance curve, knowing this maximum inductance, we can decide a lot of choices, like where to place the power layer, how many decoupling capacitors, and then make this PDN satisfy this target impedance. You can see that this is, again, the 20 dB per decade curve. That's the inductive behavior. So this is a simple illustration for multi-layer PCB board. There is this is where the high frequency matters the most, between the power ground layer and then the actual IC package. And then we have a pass to the decoupling capacitors and pass to the decoupling capacitors. And then here we have a power ground layer. So we can build a physical model, physics-based model, to model all this geometry. But at the end of the day, what we can see from this complicated circuit is actually very simple, right? So this is not a physical model. We say it's a topologically correct behavioral model, because it just mimics the behavior, not the physics. But we can connect this to the basic understanding. So first, the C curve is from the C decoupling capacitors, and then we see the effective inductance of this board design. And then we see the capacitance of the C power ground plane, and then this inductance is between the power ground plane and to the IC. So that is where the high frequency, the most important inductance for the high frequency. How many minutes? So let me skip all of these presentations. So it's about basically the demonstration of that basic concept in more realistic high multi-layer PCB design. There are many possible design choices, but we can choose the best solution based on the same physics, tracing the current path and minimize the current, minimize the inductance. So let me touch on this design guidelines for the multi-layer PCB design. So this is a very typical curve you may see for any complicated board. So high frequency here is mainly governed by the geometry between the power ground layer and PCB, the power ground layer and the IC. So adding decoupling capacitors doesn't help for this high frequency. So each frequency, there's a specific geometry that can reduce the PDN impedance. So if you want to reduce this region, adding capacitors doesn't help at all. Only way to reduce this inductance is to add more vias between the power ground plane and IC, or place the power layer very close to this IC, so that we can reduce the inductance between this IC and the power ground plane. And after that, we see this C-plane curve. That's from the parallel plate capacitance between the power and ground layer. So if you add some special materials, high decay materials, you actually can lower this impedance like this, or make this layer very thin. Then we can increase this capacitance, lowering this impedance. And after that, we see the effective inductance of this entire board from decap all the way to the IC. So having multiple decaps can reduce the inductance to the IC, or having lower ESL, or having more vias. All of this can help to reduce this region. And then the low frequency is dictated by the total capacitance. So if you add more capacitors, then we can lower down this impedance profile here at this range. So takeaways, again, it's the current path governs that PDN profile. So inductance is important, and then we can, based on this target impedance or the given inductance value, we can choose the many design options to satisfy this target impedance. And then key factor is the area and length. We want to reduce the length or reduce the area so that we can minimize the inductance, or having multiple paths. So by having multiple paths, the inductance can be reduced a lot, right? So we have parallel path, maybe n parallel paths can make the inductance n over n. So this way we can reduce the inductance a lot. Yeah, that's it. Thank you. Thank you for your attention.